It's not easy to prove the chain rule, so we'll just do the proof for one case. We'll do it for the case where g of a is not the same as g of x. So the chain rule in its statement is that h prime of x is equal to f prime of g of x times g prime of x, for h of x being the composite function f composite g of x. So let's just run through it real quickly. Assume that f and g are differentiable functions and h of x is the composite function f of g of x. Okay, let's take the derivative of this composite function using the limit definition. One of the limit definitions that we're familiar with, h prime of a, we're doing this for a, is equal to the limit as x approaches a of h of x minus h of a over x minus a, which is the same as replacing h of x, is the same as the limit of f of g of x minus f of g of a over x minus a. And now we're going to multiply by a strange form of 1, which we like to do sometimes when we're making proofs. So we have the original limit of the quotient function f of g of x minus f of g of a over x minus a, but we multiply that by g of x minus g of a over itself. So that's just 1. It's legal to multiply by 1. We're not changing anything. And we're doing it because we're going to move things around in here with a commutative law of multiplication to get it set up to say what we need it to say. So here we're just going to swap the position of the denominators, and we get the limit as x approaches a of f of g of x minus f of g of a over g of x minus g of a times g of x minus g of a over x minus a. And as I said earlier, that's just an application of the commutative law of multiplication. Okay, so now we're going to distribute the limit. We have the limit of the first factor times the limit of the second factor. And we get the limit of f of g of x minus f of g of a over g of x minus g of a, that's the first limit, times the limit of the second factor, g of x minus g of a over x minus a. Now, we assume that g of x is differentiable. Thus, we know that g of x is continuous. And if that's true, then the limit as x approaches a of g of x is going to be equal to the limit, the value g of a. Or ignore that other stuff. You see, I made a mistake, so I went back and crossed it out. Now, we assume that g of x is differentiable. Thus, we know that g of x is continuous. So that means, by definition, that the limit as x approaches a of g of a is equal to g of x. Another way of writing that, let me do it the regular way first. The limit as x approaches a of g of x is equal to g of a. Another way of saying that is the value of g of x approaches g of a as x approaches a. Now that's important because I want to change the notation of my limit. So we're going to rewrite the line up there. We're going to rewrite it as h prime of a is equal to the limit as g of x approaches g of a, because we just argued in the brackets that that happens as x approaches a, so we can write that of f of g of x minus f of g of a over g of x minus g of a. What is that? That looks familiar. Times the limit as x approaches the old a as before of g of x minus g of a over x minus a. What is that first limit? Look at that. That is equal to f prime of g of x. Just look at it. The other one's obviously g prime of a, but f prime, it's not going to be at a, it's going to be at g of x. And the reason we're able to say this about these two functions is because both f and g are differentiable functions. If they were not, we could not say that this is equal to f prime of g of x and the other one's g prime of a. Thus, we have shown that h prime of a is equal to f prime of g of x times g prime of a. But a is just a dummy variable here, so we can have it be anything. We're just going to say it works for all a's because a was a dummy variable. It wasn't an actual value for x. It was a dummy variable. So it's going to work for x. So we can rewrite this as h prime of x equals f prime of g of x times g of x. Not going to ask this question on a test, but it's nice to see.